Okay, today's lesson is on inertia, or what is also known as Newton's first law. Just want to go over an overview of what you should have out with you. The first thing I would do is navigate to this page. Obviously, this is where you found the video. And then when we are talking about this, there's going to be three things we're going to do. We're going to look at a PowerPoint lesson, which is this lesson here, and I'm going to go through the PowerPoint. We're going to do a reading on mass versus weight, and we'll talk about that shortly. And then we're going to do a consolidation of Newton's first law. And I want to direct your attention to the law of inertia is stated here as well on the page. There's some conditions, and there are 4 or 5 videos that some of them we're going to watch in this video tutorial. And the other ones I would urge you to go watch, especially this Khan Academy one. It's a good one to go watch as well. So get out a piece of paper and a pencil, and this is a really important lesson. Inertia is one of my favorite things. It explains so much of the world. If you can understand the concept of inertia, then you are actually able to understand situations and physical behavior of objects in the real world very, very well, all the way from biology to engineering to physics to chemistry to sports to everything is somehow related to inertia. Often people mistake inertia with something called momentum. In grade 12, you learn about momentum, which is a vector quantity of mass times velocity. It has a numerical value. Inertia is not that. Inertia does not have a numerical value. However, there are indicators of what inertia is and sort of measures of it that are anecdotal. Not so much anecdotal, but they like we could talk about mass as a measure of inertia, and we'll see how that plays a role in just a few minutes. However, just be aware that this is sort of a game changer, and when you're going to hear this word inertia, and you're going to start thinking about it when you're driving cars, when you're walking, when you're doing anything, you're going to understand, oh, that's what inertia is. Now, it's too bad that we're not in class doing this. There's tons of little experiments we can do and just have fun with it. Unfortunately, we'll do it this way for this year, and then we'll move from there. Okay, so let's go take a look at this here. Okay, so Newton's first law. Now, write down at the top of your notes, law of inertia, Newton's first law. So here's what inertia is. Normally I would do a bunch of experiments to show you this, but you'll just have to get it from here. So inertia is a measure of an object's resistance to change in motion. Okay, and you're like, well, okay, let's write that down. That is legitimately what it is. It's inertia is a measure of an object's resistance to change in motion. Now, there are 3 things that are offshoots of that. You probably heard about this in the Magic School Bus. An object at rest tends to stay at rest. An object in motion tends to stay in motion. And an object's motion is only changed if an external force acts on it. So, if you find a bowling ball on the ground, and let's say a bowling ball, like a massive big rock just sitting on the ground, or even on ice. Let's say that there's a huge rock sitting on ice, okay? And there's a little pebble sitting on the ice. Both of those objects, if they are stationary, want to remain stationary, which means that you require a force in order to get them to accelerate and start moving. Now, if you've ever seen curling, or you've played hockey and you see a puck move, or or you think about even pushing these rocks on the ice, you know that once those objects are moving, they will continue to move. Now, of course, they slow down because there is an external force acting on it, and that's friction. And friction acts backwards on the object, which slows the object down to a stop. But when those objects are at rest, their tendency in this universe is to just sit there and not move. And once they've been pushed and put into motion, their tendency is just to keep moving at that speed forever. Now, of course, as I said, the external forces of friction, maybe the wall at the end of the arena, those are forces that will stop it from moving. But in a frictionless environment, where there's no walls and no friction, that object, once in motion, will just go forever at that exact speed that it was going at. Now, I think you can kind of grasp that idea, and it's not that hard to sort of just get into your mind. Now, some things like to stay at rest more than other things, and some things like to stay in motion more than other things. Okay? So that's where you'll see here that mass is a measure of inertia. Okay, now this means, and I wrote here that inertia can be better formalized as a resistance to change in motion. We actually wrote that up here. Now, here's the thing. The more mass an object has, the more inertia it has. Not weight. I didn't say weight. Mass and weight are two different things. And in your reading today, you're going to read about the difference between mass and weight. And it is a very, very important distinction to make. So when I say something has mass, that's a kilogram. That's a mass. That's a fundamental product or value or measure of nature. Weight is the effect of gravity on a mass, and it changes depending on where you are in the world and in the planet and in the universe and on different planets. But the mass of an object will remain the same. So the more mass, the more inertia, which means that there's more resistance to change in motion. So let's go back to our little rock experiment. Big heavy rock like a massive boulder sitting on the ice and a tiny little pebble. If I said to you, go up and kick those two, you're going to walk up and you'll kick the pebble, and that pebble has very little mass, therefore very little inertia, which means it has less resistance to change in motion. So therefore, a small external force will get it to move quite quickly. Now, the big object, you're not going to want to go kick it because it's at rest, and because it has so much mass, it has a lot of inertia, a lot of resistance to change in motion. So therefore, that rock will just stay there, and you'll kick it, and even though a sizable net force will barely get that object to start moving, which means that it has more resistance to change in motion. It's less likely to want to change its mass or its motion. Same thing can be said for objects in motion. Okay, let's think of a transport truck going 100 kilometers an hour on a highway, and a motorcycle, or let's just say a small car going 100 kilometers an hour on the highway. If both of those objects slam on their brakes, the truck is going to take a long time to come to rest, whereas the car can stop very, very quickly. And you imagine an icy condition, that truck is just going to keep moving very, very fast for a very long time because it has so much inertia that it will continue that motion, and the net external forces of friction are small enough that it would just slide for a very long time. Whereas a car with less mass or less inertia is going to slow down much quicker because it has less inertia. This is why it's hard to stop people who say, like, it's a runaway train. A runaway train is a dangerous thing because if a train is going too fast, it has so much mass, tons and tons, thousands and thousands and thousands and thousands, tens of thousands of kilograms of mass. Once it's in motion, it's very, very hard to stop that thing. And so it can slam on the brakes all at once, but it's going to take a long time, kilometers to stop. This happens with if you think about a small canoe. If you're in a canoe, has very little mass, and you're going forward, you just put your paddles in the water and you just come to a stop really quick. Take an aircraft carrier. An aircraft carrier going, let's say, 40, 50 kilometers an hour forward, when they put on the brakes, if they were just to turn off their engines, it's going to take kilometers and kilometers to stop because it has so much mass, so much inertia, it's going to take a lot of effort to stop it. It's also why if you're playing baseball, let's say that someone throws a tennis ball at you, you don't mind catching it with your hands because it has very little mass, so therefore very little inertia, which means it's easy to get it to stop moving. Whereas if someone comes up and takes a 100-pound ball that's the same size of a tennis ball and throws it at you, it's going to be very difficult to catch and stop because it has so much mass, more inertia, therefore more resistance to change in motion, which means once it's in motion, it will want to continue in motion. Now, I could go on all day about this. Some other things, like when you're on a bus, imagine being on a bus. If you're stationary in a bus and it starts to accelerate out from under you, you fall down. Most people think that you fall backwards. That's a lie. You are not falling backwards. You're falling down. The bus is accelerating out from under you. Therefore, your body is at rest. You want to stay at rest, which means that your feet go with the bus, but the rest of your body takes a little bit of time for to transfer the energy up to the rest of your body, and you fall down to the ground, straight down. Somebody from outside just sees you drop to the ground, and they watch your feet pull out from under you. Same thing if it's moving at 100 kilometers an hour and they slam on the brakes. Your body's moving forward at 100 kilometers an hour. Because it's moving forward at 100 kilometers an hour, when the bus slams on the brakes, your body is still moving at 100 kilometers an hour. You go flying forward, right? You're not being forced forward. Your body was just in motion in that forward direction, and you will continue in that forward direction unless an external force like a seat in front of you, the windshield, whatever the case may be, stops you from moving. The bus was able to stop because it was using the friction of the tires on the ground to stop the whole thing from moving. Okay, now what I want to do before we talk about more examples of this and show you some examples is talking about different conditions. So we're going to start talking about these, like draw out this diagram, and then you can pause this and listen to it afterwards. So forces are balanced. Now, here's the thing. If the forces acting on an object are balanced, meaning like, let's say you're pushing forward with 100 units of force, and an object's pushing backwards on that object with 100 newtons of force, those forces are balanced. That object has two choices. If the object was already at rest, so let's say that it's that rock, and I'm pushing forward with 100 newtons or 100 units of force, and someone's pushing the other direction opposite mine at 100 units of force. If the object was at rest and the forces are balanced, there's no net or unbalanced external force acting on the rock. So therefore, it has no acceleration, and therefore it will just stay at rest. So that object will stay at rest because those forces are balanced. And that is another example of inertia. Okay. Another thing is that you could have is that the object could be in motion, meaning that it has some speed. So it says the speed is not equal to zero. Okay, well, let's say that a car is moving forward at 100 kilometers an hour. There's frictional forces and wind pushing back on the car, and then there's the force of the engine pushing forward. Now, if the force of the engine pushing forward and the frictional forces and wind resistance pushing back are balanced, the car will not accelerate. Makes sense? And if the car is not accelerating, it stays in motion, meaning that it will maintain the same speed in the same direction. That's a hard one to understand. The at rest one is simple, but people don't often realize that if you're moving at a car at 100 kilometers an hour on the highway at a steady speed, you're just moving forward at a constant speed, and that's because the forces acting on your car are balanced. The friction and air force pushing back is exactly balanced with the forward force of the engine, of the tires pushing your car forward from the gas that you're burning and all that kind of stuff. In both cases, when forces are balanced, there's no acceleration. The object either stays at rest or continues moving at the speed it was moving. And this is a corollary of inertia. Okay, now what we're going to do is we're going to look at some examples of inertia. We're also going to talk about the idea that one of my favorite ones, and the one that's going to bother you a lot, is that when you're in a car at a stoplight, you are at rest. Okay, and so is the car. When the light turns green, you slam on the gas. You feel like you're being pushed into the car or into the seat. That is a lie. That is not happening. What you don't realize is that your body has a tendency to stay at rest. The car is accelerating out from under you, meaning that the seat is pushing you forward, accelerating you with the car. So that sensation of being pushed back into the seat is fake. In actual fact, inertia is keeping you at rest, meaning that the car is pushing you forward, and that feeling of the seat is the car actually pushing you forward and accelerating you. When you're up to a big speed and you slam on the brakes and you fly forward, you're not flying forward. The car is stopping and accelerating backwards from underneath you. You just keep moving forward at the same speed. So if you were going 100 kilometers an hour and you stop suddenly, your body wants to keep going forward at 100 kilometers an hour. That's why you have seatbelts. And a seatbelt actually latches, sometimes it locks. That's because there's a mass in there, an inertial mass, that will, when you slam on the brake, the mass in your seatbelt contraption actually moves forward with the car. So when you stop, it moves forward, but the car stops, and that locks the seat in place. That locks the belt with friction. And then you just have to tug it a little bit and start moving, and that mass will move back, and it'll loosen up. Just uses inertia. So many things use inertia. Again, I could talk about this for the entire day if I had to. So let's take a look at some videos related to this. Here's a double basket skateboard transfer. So you'll see that what happens is he's moving, his board suddenly comes to a stop, his body continues moving and transfers onto the board. Now I think they try a double basket transfer. That did not look like it felt very good. They did the double transfer. All right, don't try this at home, please.
The law of inertia states that objects will maintain their state of motion unless
Abjects.
acted on by an outside force. This means that moving objects will stay moving and still objects will stay still, unless you push or pull on them. There are two safety devices in your car to protect you from the effects of inertia. The first is your seat belt. When the front end of your car rams another object, your car will suddenly stop or slow down. Because of inertia, your body will want to stay moving at whatever speed it was moving before the accident. If you're not wearing a seatbelt, this means you will hit a windshield. The seatbelt provides a force to stop your body's forward motion. The second safety device in your car is a headrest. When your car is hit from behind, the car is suddenly pushed forward. Your head will want to stay still, but your body will be pushed forward by the seat. This causes your head to feel like it is snapping back. Your head is actually staying still because of inertia, while the rest of your body is being pushed. Your headrest pushes your head forward with your body so that you don't suffer from whiplash. Look at the difference between a headrest that is properly set versus one that is set too low to push your still head forward.
Okay. Now, no making fun of me here because I have no gray hair. So this is a few years back, and so I normally do this in class, and so I've set up some. You can see here uh, cups, and the cups have water in them, so that they have inertia, so they're less likely to move. There's a pie pan. These are toilet paper rolls, and then 3 eggs. The eggs are situated over top of the cups. Now the key is because these have inertia and they're less likely to move than the pan. I'm going to use this ruler to snap the pan. It'll push it out, and because these toilet paper rolls have less inertia than the eggs, they're going to move very easily. Whereas the eggs have a lot more inertia. They're heavy. They have a lot of water in them. And therefore, you'll notice that they will want to stay at rest. And so, what theoretically should happen is you hit it, and these eggs should do what? They'll stay at rest. The pan and everything else will move out of the way, and they should drop safely into. There you go. I'll try and do this maybe if we get back to school, I'll do this for you guys. Or someone else can try it. I don't know why I hit the ruler off the thing. There's one here about Spaceballs that you can watch. Again, where they're moving forward at really fast speed and then they come to a rest. All right, you could search up all sorts of things that deal with inertia. You'll often hear about things like people who uh, pull a cloth, like tablecloths out from under, uh, like they have china and stuff like that on it, and they pull the tablecloth out and the china stays there, and that's because the tablecloth is easy to accelerate out and the other objects are at rest, so they stay at rest. All right, I want you to read about mass and measure of inertia very quickly, so you can just download this and print it out and read it. Big thing here, mass is not volume. Super important. That's a big thing. Highlight the key ideas like mass is measured in kilograms. Okay, so you want to read that. Mass is not weight. This is a big issue with people in the world, like not understanding the difference between mass and weight. And so you really need to fundamentally understand the fundamental difference between what mass and weight are. So you're going to read that. You can take a little note here about the what mass is and what weight is, and I would highlight it, but also I would take very brief jot notes about this information in here. And then you can just read over the questions and just read the solutions to those questions, although you'll probably be able to do that on your own from that. Again, do not just skip this. Please read this, highlight it, and even take some jot notes or rewrite some important points off to the side. It's very important that you understand that. Okay, how do I get back the page? Okay, so we come here, and then I just want you to do these consolidation questions. And the consolidation questions are, in your own words, describe the concept of inertia and how it relates to mass. Again, this is just consolidating what we've learned. Go back and listen to about being pushed into your seat while accelerating forward, and we know it's a lie. Explain why seatbelts are necessary. So if you're moving fast forward, what happens? Talk about the transport truck and a car both going 100 kilometers an hour, which is easier to stop, and why. Nice, short, concise answers. If you're staying in a stationary subway train, why is it wrong to say that you fell backwards? Did you actually fall backwards? And explain why throwing a baseball at a toy truck causes the truck to move and possibly get knocked over, where throwing a baseball at a tank has virtually no effect on the tank. Hence why when you're firing things at tanks, you need big, heavy projectiles to hit tanks. Whereas a baseball bat, or sorry, a baseball and a little toy truck, you don't really need that. So those consolidation questions for this lesson are extremely important as well. So please follow up with those. All right, so that's inertia. Hopefully when we get back to school, I can do a bunch of little demonstrations for you related to inertia, some little tricks you can do. All right, have a good day.